So this is the LB that I set up a few months ago. It's been running pretty good ever since then. I got a few requests to do a programming video and just a walkthrough of how I have this machine programmed. I've set up a sample program that's pretty identical to what we use for this machine. I can't really run a part because I don't want to show what we're running here, but I do have this sample program that goes through almost, it's every move identically. It works on what I run, but I'm just not going to run it with the part today. Starting out, I initialize some of my variables. I have a pallet in here, and those initialize automatically, but I also have a machine ready and a start machine variable. These two variables control when the door opens and closes so that I can use a thread to open and close the door and continue to move the robot while that's happening. Right off of the top of the program, I use a wait for orange light. That orange light comes from the light stack on the machine, and you can see my wire up there. It runs to that light stack. I have that going through a solid state relay that is connected inside the robot controller. It basically just works like a switch, and so that's how I know that orange light is on. That gets turned on whenever an end of program happens, and when that light is turned on, it allows me to bypass the wait, and then right away I set machine ready to true. I'm gonna skip the thread assignment for now, and because they're at the bottom, so I'll get to those later. Right after that, I set my gripper to open just to make sure it's open before I go to grab my stock, and then I open on a move L. I use a linear move for almost everything in my program. Joint moves are simple and they're much more efficient, but a lot of what I'm doing here is linear, like trying to grab a piece out of the jaws on the spindles or try and pick up a piece. And so I kind of just stay in linear move unless I just need to rotate a joint, which I do later on. Then I have this start point. This is kind of just my general starting area. Where it is the part sits in this rail right here, and this area is where the jaws are about an inch above the stock. When I'm in the ready position, I go to a directional move. I do this because I'm going to use the until contact feature, and so when that robot runs into anything with the until contact, it'll stop the move right there. For this, I'm using the positive Z direction of the robot, and that's just going to push that thing straight down. My tool speed for this, since I'm using an until contact, it'll actually warn you here. I use a tool speed of about 2 inches a second and the standard acceleration. And then my until contact is set, and on the same thread, I also have an until distance. So when this tool direction is running, it will go until it runs into something or until 4 inches have passed. And if it reaches 4 inches, it will just pop into the next move. But we're going to break into this force. And so if it does feel a contact, it will turn on the force function, which is inside the templates here. This force is a simple force based off the tool. I set it at 2 pounds. And I have a weight just to make sure that force gets pushed onto the part. And then I close the gripper. And then after that, I set my payload. And you can set a payload through the PhD right here. But this allows me to set my center of gravity. And setting this just helps the robot even more compensate for its own weight. After I have that, I just wait for another half second to make sure that those jaws are completely closed. And then I pop into rail retract. Again, I said that when I'm doing this direction, the until contact will trigger if the end effector runs into something, or if it doesn't and it travels 4 inches, it will pop into rail retract. The rail retract is basically 2 part heights above the rail here. That just allows me to get high enough so that I can swing into the machine and not run into the door or, another part below on the rail. I have this slow down just a little bit. I'm now carrying a payload and I'm pulling it vertically up, and I don't want that to slip, so my acceleration and my speed are reduced just by a bit. Then I have a wait until the door is open. Again, I'll show the thread later, but the point of this is that if my thread is running and the door is not completely open yet, the robot checks to make sure if that door is open before it goes into the machine so that it doesn't slam into the door. Once that's happened, I have a move L here, except I do another move so that I can switch my feature to MC. If you don't know, features are in installation and under features. This MC is basically just my main chuck. I set it up so that I have a plane and the origin is based in the center of the primary spindle. That really helps when I'm setting up, new jobs or whatever. It's easy just to grab that origin and move. Here, I'll show you. In the move screen, when I switch to MC or main chuck, it makes it super easy because the origin's already set up and my XYZ coordinates follow that. And so moving in Z plus and minus I know that's right in the center of that chuck. My next move is on center. I'm moving this just a little bit faster because I have a longer distance to move. My acceleration is just above the normal acceleration. So as you saw, I kind of went and I tucked that robot back and I just went straight from here, just straight to the point right before that chuck. After on center, I moved to MC entry, and I'm doing this at 4 inches a second. The reason I do MC entry, so when this happens, the piece of stock gets shoved into the jaws about an inch, so it's going to be right here. The reason I do that is because the next thing I'm going to do is my force function. If there were anything to go wrong here, and the robot is not perfectly lined up with the spindle, when I run that, it's going to run into this space, and it's going to error out because it's going to protective stop, and I would rather that happen than think my part is inside the spindle and clamp and unclamp, drop it into the conveyor. It's better that I just use a full force waypoint and push it into where it's supposed to go and see if I get a protective stop out of it or not. It's not the best thing to do. I mean, it'd be best to kind of feel around and make sure that you're not spiking your load before you get to your waypoint. But for me, it's the quickest way to do it. Also, if it's set up right, I don't get that many protective stops. I mean, maybe once every couple months if somebody bumps the base, but it hardly ever happens. It's just a check to make sure I'm inside the jaws of the machine. After that, I pop into my force function. Again, this is simple based off of the tool feature, and I apply a 4-pound force here. I go a little higher on the force just because I'm now carrying a little bit higher payload. I want to make sure that it's really pushing into that spindle. The next thing I do is wait for the force to be greater than 40. This is in newtons. What this is saying is that the tool right here, which I think the force sensor is in between this connection. What that's saying is it's going to push into that spindle. And when that force sensor feels a force that's greater than 40 newtons, when my part runs into the end of the chuck, the force is going to spike. I have it set for the parts that I'm running so that it spikes just perfectly. It sets off this force is greater than 40, and then I can continue down. If that doesn't happen, the robot will just sit there. And since someone's operating next to these machines constantly, because we have a robo drill right next to it, it's easy to look over and, see if the robot's not doing anything, it'd be caught in this position. I've only ever had it catch in this position a couple of times, and I probably should throw an exception if it waits for too long of a time. I don't have that happen very often, and when I do, I just turn the force down so that it accepts a lower amount. After that, I have a wait of half a second in case I have any bounce, if it hits the back and it bounces and then it forces back in, because my force function is still running, so I give it a half second. Once that happens, I open the jaws of the robot and I close the main chuck at the same time. Now I'm using a pulse here because I have wires that are going directly to those foot pedals, the same way it's through a relay set through the foot pedal. It acts like a switch would. The foot pedal doesn't know the difference between the robot triggering it and you pushing it with your foot. What this does is I have my 4 pounds of force on the part. The robot is open now and the main chuck is closing. Say that part was kind of at an angle inside those jaws, it's going to get slammed into that chuck for, straight and flat, and then the chuck's going to grab it. This kind of setup you do have to be careful with. You have to have enough force to be able to keep that part in there and run enough trials to know that it does indeed straighten out. If your stock is cut crooked, this is not a good idea. You're going to clamp your stock at an angle, and then when the spindle turns on, it's going to wobble. If I have crooked stock, I will keep my robot closed, and I'll close the machine. So then I wait a second just to make sure that the machine chuck does indeed close all the way. And once that happens, I break into the MC retract. Since I don't have any stock in the robot, I do an 80 acceleration and 40 inches a second. You can see the robot moved forward. I forgot to go to the MC entry right there. So there's MC entry. And then once the force triggers, the robot would move forward even more. And then once that's all done, it would move straight back to MC retract from wherever it's at. After this, I do a check to make sure that the stock is set inside the spindle correctly. How I do that is I close the gripper on the robot, and then I go up to a position called part check. Now, this position is very, very close to the part. These parts have a chamfer on this edge, but this part is sitting right on that chamfer. The point of it is if that part, or if the stock is not embedded in the jaws all the way, it will touch the space and it will trigger because I have an until contact set on that part check. If it goes up and it hits the part, then it will run an until contact, and then it will call an event, which this is set up as a subroutine, and I have just MC event 1. Again, I will scroll down and show that once I finish. If I don't contact anything, I pop into a move J. I'm not carrying any payload right now. I need to rotate around to the back chuck, and I just got to use a quick move. So for that, I'm going to use this move J. The first move I do just backs up the robot and rotates a tiny bit. And then the next move I do spins my fifth joint 180 degrees until I'm lined up with my back chuck. You can see these two moves are running very quick. I'm running max speed on my joints and 250 for my acceleration. Then I pop back into a move L. These are still on the main chuck feature. Everything that I have programmed inside the machine doors is programmed off of the main chuck feature. So for a second, the reason I do that is, say I had a major move here, I had to rebolt this, or the machine moved or something. Well, I can go back, reset my origin, and everything is going to be back relatively close to where it should be, and all I'll have to change is the Z value on the robot to line everything back up again if there's a major move on any of this equipment. So now that I'm on that second spindle, I'm going to do a directional move. I'm doing Z negative now, but I'm also using my main chuck feature, and so I'm going the other direction. Again, I'm running 2 inches a second because I'm entering a move and using this until contact. Same setup here. If I travel 4 inches, it's going to kick it out. If I contact anything, it's going to break into more code. I do a 2-pound force this time. I'm going to wait half a second. I'm going to open the jaws this time. This I have an ID grip for. It's kind of hard to see, but I have little pieces in here, and it grabs onto the inside of a bore. So then I wait just a quarter second just to make sure that the jaw opens. And then I trigger the sub chuck so that it will open up. And then I wait another second to make sure that it's completely open. And then after that, I pop onto, this is at 20 and 30. And notice that this is a linked, some of the other points in here are linked. This one is linked too. So SC on center was used as a joint move, and now it's used as a linear move. but it's the same point because it's just in front of that chuck, a safe distance away from it. After that, I do a chip dump. So like I said, I have a bore on this. I'm going to accelerate. Here, I'll show you what I'm going to move to first. So you can see that robot turned up, you know, kind of vertically. It kind of pulled back away. In order to pull off this chip dump correctly, I use a kind of a little bit higher speed, but definitely a higher acceleration. And what that does is I parts here and I jerk it backwards, and all those chips will fly out. So I'm going to note that on this chip dump move, I'm pretty confident in my gripping pressure and the weight the part is low at this point that I'm not going to throw my part out of the robot gripper. So I've dumped the chips. I'm ready to exit the machine now. So I pop back into a move J and I switch the feature to a base. And I've also reset the speeds for this move in the move itself instead of, you know, setting it in each waypoint. I'm doing 120 and 200 acceleration, just a little quicker. I'm not carrying that much weight now. I mean, it's still a payload, but I'm not carrying a whole lot of weight, and I'm confident in my gripping that the part will stay. The first move I do is a machine exit. So you'll see that I bring that part around and I face it out inside the machine. The robot is now clearing the door. I actually move this joint speed just slightly higher, but I keep the acceleration. And I also bend with a pretty large radius on this move so that I can, you know, continually move that robot without it having to stop. Once it's reached that point, I set the start machine to true. That will run another thread down below to close the doors on the machine while the robot is moving. From there, I do a table approach. The table sits right here. It's this blue table right here. We have it sit right here in between these two mats, and we set down, I don't know what it is, 3 or 4 parts on the table. There's an operator here running this robo drill all the time while this lathe is running, so we don't get parts built up. You just press pause on the robot if you do. So this is kind of a general area up high above that table. Now it can drop down into any position on the table. So along the backside of this table here, this is where the robot has access to. You can actually kind of see the outlines of the parts on here. So we'll drop one here, 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 here. So it looks like 4 parts. So then I have my pallet set up in the templates here. And the pallet setup isn't too hard. I mean, it essentially runs you through every single step you need to do. The only difference I have is maybe my tool action point is where I have an until contact, or if I reach the tool action point, I'm essentially guessing that, hey, there's no table there because I didn't contact anything. So I run a pop-up warning that says there's no table, and this pauses the robot and it won't drop the part. At this point, if there's no table, you'd have to stop the program here and get that part off the robot. It's just an error exception so that I don't drop a part on the floor. Then for my tool action, I wait half a second, and then I close the gripper. Remember, I have an ID grip here, so I'm releasing the part, and then I wait again just for a little bit, just to make sure that I'm not going to rip the part up as I'm closing the jaws. And then I go to my exit position. So we'll run through these positions just so you can see where they're at. So my approach is, and then my tool action point is just a linear move down, and then my exit point is just up a little bit. You can see that I'm pretty stretched out here. I'm almost at my max reach, but we actually set the robo drill in this particular position so that we could have a nice walkway and be at the very end of this robot reach. And so then after I'm done with that, I go back to my table approach position just to go to a high spot so I don't swing through the machine or the table. And I run this quick because I don't have any payload on, there's nothing on the robot. And then I swing back around to my start location. So that is the full program, and now I'm going to run through my the event and the 2 threads I have. First one I have here is the event where this part check gets triggered. And so what happened in this case is that the robot tried to move forward. It ran into the part, which is telling me that, hey, the part's probably not set in the jaws all the way, or the part's too long. What's going to happen in this scenario is that I have just a list of waypoints set up. They're not named. This is just something quick that I made. It's just supposed to get the robot out of the way. So I run some waypoints. Here, I'll actually run it. So I run some waypoints. I'll run it from here. So I have that robot moving out of the way. So then my pop-up comes up. It says check part in main spindle. The robot has paused right here, completely out of the way. That way anybody can come up, easy into the spindle. The robot's not in your way. Once you verify that part's correct length, or it's all the way in the machine, all the way in the chuck, you can hit continue, and that robot's going to spin back around and go inside the machine. So yeah, it moves back to the waypoint 2. From there, when it's actually running, it will just spin around to the sub chuck. We've done our check. You've checked it for the robot now, so it's just going to continue and go to the second spindle. So now I'm going to move down to my 2 threads. This first one is for the machine ready. You can remember at the top, after my light is triggered, I set machine ready to true. What this does is I have a wait for machine ready, so that is checked off. And then what I do is I wait half a second. The reason I do that, if you pull the door when the right light turns on, doors won't open. That latch up there takes like a second to unlock. And so what I'm doing here is that I just wait half a second, once I've received that signal, make sure the latch is unlocked, and then I set the door to open. Then I have a magnetic switch on my air cylinder up here. You can see one of them, the other one's on the back side, but it's just a little reed switch. I have a magnetic piston in there, and that triggers once the door is all the way open. And then I wait 2 seconds, and then I set that valve, which is this valve right here. I set that valve to, turn off, and then it releases all the air pressure, and then I switch this back to false. So while that's running, the robot is grabbing the piece of stock, and then they link back up right here, and then the robot is like, yep, the door is actually open, and it continues. For the start machine assignment, it works identically. I mean, I exit the machine, I set start machine to true, thread 2 starts up, and just so you know, the threads are in the advanced section right here. So I start up the second thread, door closed turns on, and then I wait till my door sensor. Then I turn off the valve, I wait half a second, and then I hit the button, which, the button is linked up the same way that the light is, just wire going through that control right there. It's through a relay, and it basically just connects the wires that same way that you would if you physically pressed it. So then I set it back to false. I set it back to false so that this thing doesn't just continually run, because it will. All right, so I've basically run all the way through the program. I'm going to set this back to. So that's the full program. I try and do things as advanced as possible to save the most amount of time. Doing those threads saves, quite a bit of time, because you're not executing the door to open while the robot should be moving. I've seen setups before where the robot doesn't move at all. They open the door and then the robot begins moving, and it's like, well, I mean, that just takes up. It might only take up 10 seconds, whatever. But throughout a day of process, that's a lot of time, and those 5-10 seconds may add up to a couple hours over a few months, or even a couple weeks, maybe even days, depending on your cycle time. And I'm trying to mitigate as much downtime as I possibly can when I run this robot. So the machine's on manual right now. I'm going to shut the doors, and I think I'm going to run through this. There's not going to be any part moving around. The door is going to open and close, but nothing's going to, I'm not going to be moving a piece around, just to show you the speeds of the thing. So in order to run this, I'm going to have to manually do this, and I have to skip the orange light check, and I'm going to go straight to machine ready. Let me close the doors. So I'm going to go straight to machine ready, and I'm going to run that. So no table, okay. So there it is. That's the full thing. The only other thing I'd have is, like, I run this robot quick. I have seen videos of guys running the preset speeds for this robot. It is a collaborative robot. I get the point of that. But also, they gave you 180 degrees per second to work with. And I know that it doesn't run that fast all the time, depending on your payload, and where you're at in your reach. It's not a slow robot, but many people use it as if it's a slow robot. I don't believe in that. I mean, I know this robot's running brushless motors. I know it's also running harmonic drives. It can handle the speed. I mean, the engineers designed it for that speed. Now that it's the speed, the acceleration is a different thing. The linear acceleration, here, okay. Linear acceleration can go up to almost 6,000. That is super high. I mean, that is ridiculously high. The max I do on here is 150 linear acceleration. Maybe in my total time of programming these robots, I've hit maybe 200. It's stupid high. The robot is jerking at that point. You're not saving any time, so we'll go check the joint accelerations. So almost 2,300. That's also ridiculously high. Max joint acceleration I have ever done is 400, and that's without any payload or anything. And it is quick, and I think 400, could be reasonable in some situations. But if you're just moving the robot around like I am, doing a process like this, the accelerations don't need to be maxed out, shouldn't be maxed out, because that's a good way to destroy the gear trains in this thing. But if you can accelerate, go full speed. I mean, why not? I mean, if you're not going to throw your part out and you have the time to accelerate, you might as well go full speed. From what I know about machines in general is that speed will not hurt anything, acceleration does. And the accelerations on this robot, they can get ridiculous. This time when the robot comes out, I'm going to place my hand under it so that it... Alright, that's kind of how I program all of our UR robots. But if you have any questions, let me know. I'd like to answer them.